Alright, so we're ready now to study gravitation, and we're all familiar with Newton's law of gravitation that says that if I have two objects of masses m1 and m2 separated by some distance r, then the force between the two is given by the relation g m1 m2 over r square. Okay, now realize that this gives you the magnitude of the force. The forces are, however, equal and opposite. Okay, and that's why we have the relation f12 equals f21. Okay, well, negative f21, and so this gives us the equation to find the force between two particles of masses m1 and m2. Okay, we are interested in asking what happens when you have an extended object. Like, what is the mass, what is the force that a shell exerts on another object. Okay, so let us consider we have a shell of, let's take a thin shell, and we're going to derive some really useful results while we're doing this. We have a shell, and let the mass of the shell be m, and let the thickness of the shell be t, let the radius of the shell be r, and we're going to say that t is much smaller than r, so we don't have to worry about that aspect of it. And we have another mass m, okay, another particle of mass m that is at a distance of x from the center of the shell, and we want to find the force that the shell exerts on this mass m. Now, in order to achieve this, what we'll do is we'll break the shell into rings, okay, and we'll use the property that every ring, okay, whose axis coincides with the line joining the center of the shell to the mass. Okay, so if you were to take rings such that the rings are located like so, okay, then each point on this ring is equidistant from the mass m. Okay, and we can figure out this distance between any point in the ring and the mass m. Let us call this angle phi. Let us call this angle theta. And if the total distance is x, if this distance is x, okay, then we can figure out what the individual distances are. What we know, I'm going to draw this in red. What we know is that this distance is going to be r sine theta, and another one here, this is going to be r cosine of theta, and as a result of that, this is going to be x minus r cosine theta. Okay, so that gives us the distance of any point in the ring. As we can calculate that distance, let's just call that L for now, and what we know is that L will be equal to square root of r sine theta square plus x minus r cosine theta the whole square. And if you simplify this, what you'll end up getting will be r square plus x square minus 2xr cosine of theta. Make sure that you obtain this relation. So this gives us the value of L. Okay, now what we also need to know is what is cosine phi and sine phi in terms of theta. And before we move on to the calculation, let's also figure that out. Cosine of phi, okay, cosine of phi is going to be equal to x minus r cosine of theta divided by L, which is square root of r square plus x square minus 2xr cosine theta. And we know sine of phi also is equal to r sine theta divided by all this, the radical. Okay, so we have all the components here. Now let's look at this problem a little more carefully. If you take a part of look at the ring rather. If you look at this ring, okay, and we have now this particle of mass m. If we look at the top part of the ring, okay, take some element of tiny mass m, then the force due to that part is going to be pointing towards the ring. Okay, in a similar manner, the force due to the bottom part will be pointing again towards the bottom part of the ring. And if we were to look at this, okay, all the forces due to all the parts of the ring will actually end up forming a conical surface. Okay, so all these forces, they form a cone, and what we realize is only the horizontal component of these forces will survive. All the components along the direction perpendicular with the axis will all cancel each other out. So the only component that survives will be the horizontal component, and so the only force that we need to worry about is going to be the force along the x-axis. So this is the only force that we need to worry about. Okay, so having said all this, what we know is that we can write down the equation for the force. So let's just call this dF due to the ring is going to be equal to capital G times dm of the ring multiplied by m divided by L square. Okay, and the only force part that contributes is the cosine term of the force. Alright, so make sure that you understand this part, and then once you understand this, the rest of the stuff is simply, calculating the force correctly. Okay, now in order to figure all the rest of the stuff out, we need to first find what dm is, which is the mass of the ring. Okay, so dm ring, if you look at the structure, it is going to be equal to the volume of the ring divided by or rather multiplied by the density of the ring, of the shell. Okay, now the density of the shell is the mass per unit volume of the shell, and it is mass divided by 4 pi r square times t. So this is the volume of the shell, and now we can multiply this by the volume of the ring, which happens to be 2 pi times r sine theta. Okay, because that is the circumference is r sine theta, so it's 2 pi r sine theta, which is the length of the ring, multiplied by t, which is the thickness of the ring in one direction, and then multiplied by r d theta. Okay, so this now gives us the total volume, the total mass of the ring. Once I have this, we can simply plug this into our equation for dF of the ring. So dF ring ends up being equal to G times m divided by 4 pi r square t times 2 pi r sine theta times t times r d theta. Okay, this is all dm multiplied by m. Okay, multiplied by cosine of, I'm just going to leave it like this because there's no room to write anything else here, divided by L square, which happens to be r square plus x square minus 2r x cosine of theta. Okay, in fact, you know what, while I have this, let me just replace cosine phi. Cosine phi is replaced with what, x minus r cosine theta, so it will be x minus r cosine of theta divided by square root of r square plus x square minus 2rx cosine of theta. Great. Now the numerator will simplify to the following. First, let's get rid of some of the terms. The pi and the pi cancels out. This r is actually a capital R. Okay, so this r, and then the r square comes out. The t also cancels out. Okay, the 2 goes away, and I have left with the 2 here, and the m stays. Okay, so what we are left with is G times capital M times lowercase m times sine theta d theta, okay, divided by 2 times r square plus x square. Oh wait, there is also another term, x minus r cosine theta, and divided by this to the power 3/2. Okay, so this is this seems to be a fairly intimidating expression, but you'll see that it simplifies out really well. So this is all the force due to the ring. Now once we know the force due to the ring, to find the force due to the entire shell, all we're going to do is integrate over all these forces, okay, due to all the rings. And in the integral, essentially it translates to integrating over theta, and theta will go all the way from 0 to pi. So let me pull out all the constants out of the integral. I have gmm over 2, and then we have integral of sine theta times x minus r cosine theta d theta divided by r square plus x square minus 2xr cosine theta to the power 3/2. Alright, great. Okay, so now we are going to use the substitution rule, and what we'll say is that r square plus x square minus 2xr cosine of theta, all this be equal to u. Okay, now if this is equal to u, then we can differentiate both sides and we end up getting 2xr negative, or that will become positive. So it becomes minus 2xr minus sine theta d theta equals du, and so this gives me sine of theta d theta equals du divided by 2xr. Now also, since we've made the substitution, we need to put our limits. By the way, the limits here were from 0 to pi, so we now need to replace the limits. So when theta equal to 0, okay, we notice that u ends up being equal to x minus r the whole square, and when theta is equal to pi, okay, u ends up becoming x plus r the whole square. Okay, so make sure that you figure those parts out. Now that we have this, my f becomes gmm divided by 2 times the integral of x minus r the whole square to x plus r the whole square. And then I'm going to replace. Now sine theta d theta is equal to du over 2xr, so I have du divided by 2xr. Okay, x minus r cosine theta, so now I got to replace it with x minus r times. Now if you look at cosine theta from this expression, it is equal to r square plus x square minus u divided by 2xr. Okay, and then that divided by u to the power 3/2 is what we end up getting. Now that we have this, let us simplify this. Let us pull out gmm over the 2 comes out, so we get 4xr, and then inside the integral I have again x minus r the whole square, x plus r the whole square. And now we can simplify this expression here. You see that the r, one of the r will cancel out. We have a 2x here, so this gives us everything inside the parentheses gives us 2x square minus r square minus x square plus u divided by 2x times du over u to the 3/2. This ends up being gmm over 4xr, x minus r the whole square, x plus r the whole square. And now the 2x actually comes out, so I can write this as 1 over 2x. Okay, so we can get rid of that, and then inside what we end up getting is x square. One of the x square cancels out, so you get x square minus r square divided by u to the 3/2 plus u divided by u to the 3/2 du. Alright, so we're very close to the answer now. Okay, so this ends up becoming gmm over 8 x square times r times the integral of x minus r the whole square to x plus r the whole square. Okay, x square minus r square times u to the negative 3/2 plus u to the negative minus 1/2 du. Great. Now you can split this up into two integrals, gmm over 8 x square times r. Okay, the first integral is x square minus r square. We can integrate u to the minus 3/2 and we end up getting u to the minus 1/2 divided by minus 1/2, plus we can do the same with the second one and you get u to the 1/2 over 1/2, and we're going to integrate both from the limits of x minus r square to x plus r the whole square. Great. So now we get gmm over 8 x square times r, and the first term here will become negative 2 times x square minus r square and divided by u to the power minus half, which gives us oh no, we're going to rewrite this as times, so we're going to have to evaluate u to the minus half at each of those two limits, and we end up getting 1 over x plus r minus 1 over x minus r, okay, plus 2 times x plus r minus x plus r for the two limits. Great. So this gives us gmm over 8 x square times r, okay, times the integral of negative 2 x square minus r square. Now this inside here will end up becoming minus 2r divided by x square minus r square plus 2 times 2r. Okay, now if you look at this expression, what happens is gmm over 8x square r, okay, the x square minus r square cancels out. You have plus 4r here and plus 4r here, so this ends up giving you 8 times r, and so the entire expression ends up becoming gmm over x square. So this is very useful. Okay, what we've said is that the force due to a shell on an object outside it is simply equal to 8 gmm over x square. Okay, now in a similar manner you can show that if instead the object was inside the shell, okay, the particle was inside the shell, then the force will be equal to 0. So do the integral and figure this out. Okay, but what it shows is for the outside part, the only thing, the expression ends up becoming the same as it would be between 2 point particles. Okay, so if you have two spherical objects, okay, some distance from each other, then the force is given by this simple expression, which is equal to gmm over x square. Okay, so we'll use this a lot in future problems to come.